Hello everyone. I just wanted to make a brief video demonstrating how to use JMP to compute probabilities, specifically from the binomial and standard normal distributions. So if we take a look at the binomial distribution calculation first, let's start with a little example here where suppose we know that 10% of a certain population is colorblind. If a random sample of 25 people is drawn from this population, we might want to compute some probabilities associated with those particular outcome. All right, so we got a couple of questions here. We want to find out the probability that 5 or fewer will be colorblind, exactly 6 will be colorblind, 20 or more will be colorblind. Okay, so in the old days, we might have to go to a table, and that involved having to learn how to use a table, and the table would be limited as to the options that could be considered for computing those probabilities. And there really is no reason to do that now. We have software that will compute these for us, so we're going to make use of software to do that. We're using JMP here, so I will open my JMP home window. And in order to compute these binomial probabilities, I will first go to the File menu and select a new data table. So this brings up a little spreadsheet, and this is where I'm going to keep track of my calculations. So first of all, from this binomial experiment, it's important to remember that the possible number of people that are colorblind from our sample of 25 is 0 if none of them are colorblind, possibly 1 or 2 or 3, all the way up to all of them being colorblind. So I'm going to create a column here that lists all of those possible outcomes. So I'm going to call this column X, and it will start with 0 and 1 and 2, and I could go through the process of typing all of them in here up to 25, but JMP actually has this really cool fill feature where if I highlight this sequence that I'm creating and then right-click on it, it brings up a shortcut menu, and under Fill I can select Continue Sequence To, and that will just populate the rest of those cells for me. If I continue to row, it's actually going to be to row 26, so it's asking me how many rows here, not necessarily what is the number here. So to get the X up to 25, then I tell it to continue to row 26. If you put 25 in there, that's okay. You'll just notice that when you come down here, it stops at 24, and so you'll want to manually add that 25th row. Okay, so there are all of my possible X values. Now, what I want to do is have JMP compute the probability of observing all of these X values. So in the second column, I will highlight that column, and up here under the Columns tab, select Formula. I'll find the Discrete Probability option, which brings up a menu of several discrete probability distributions. I want to select this binomial probability, and it asks for some information here. What is the success probability? So in our example, that's 0.1. What is the number of trials? In our example, that's 25. And then what are the X values? It calls it K here. But what are the X values that I would like to have it compute those probabilities for? Now I could put in 0 or 1 or 2 up to 25 in here, but I've already got them listed here in this entire column, and if I select that as X, it will compute it for every one of those in the X column. So now what I'm looking at here is the probability that none of the individuals in my sample are colorblind is 0.0718. The probability that exactly 1 is colorblind is 0.1994. and so on. So I have the probability for each of those x values. And you can see that these probabilities, because the success probability is kind of small, the probability of getting a large number of colorblind individuals in my sample gets really small, like close to 0 here. Okay, so that's how we can compute the probability that my binomial random variable is exactly equal to value in this x column. Now, you'll remember that some of our questions were about the probability that x is less than or equal to some value or greater than some value. So we could, the question we were interested in was the probability that 5 or fewer were colorblind. So we could just take these and add them up in our calculator, or we could be smart about this and continue to let JMP do some of the heavy lifting for us. So I'm going to create a new column here that is the probability that x is less than or equal to the values in the x column. And I will just select this column again, and under the columns tab, select formula. And now I will still go to discrete probability, but instead of selecting binomial probability, if I select binomial distribution, the default for JMP is to compute what is called the cumulative distribution for this binomial random variable. So it still wants the success probability 0.1 and my number of samples, or the number of trials, and then I will give it this x column again and click OK. And here I have the probability that 0 or fewer individuals in my sample are colorblind is still 0.0718. But now this probability differs from the one in this column, because this is giving me the probability that x is less than or equal to 1, whereas this one was the probability that x is exactly equal to 1. So there's a 27.12% chance that I will have 1 or fewer subjects that are colorblind in my sample. And so to answer my question about 5 or fewer, that probability is 0.9666. Okay. This gives me the probability of less than or equal to x. Similarly, if I want the probability of being greater than or equal to x, I can just create another column, say x strictly greater than x. And what I'll do is I will take 1 and subtract this column from it. And so if this is the probability that x is less than or equal to x, then 1 minus that will be the probability that x is strictly greater than that x. So I'll come back here to the formula option under the columns tab, and I will select subtract, and here I'll put in 1, and I will subtract off then the cumulative probabilities. Okay. And so now here I have the probability of being greater, that there are greater than 1 or more people in the sample that are colorblind. This is the probability that 2 or more in my sample are colorblind. So now I can use this to answer my questions. Going back to the PowerPoint, I'll just kind of bring up this table. The probability that 5 or fewer are colorblind is answered by this probability, 0.9666. Exactly 6 would be colorblind is answered by this probability, 0.0239. And the probability that 20 or more will be colorblind, well, that gets pretty small. That probability is 0. And so I can write these down, 0.9666 and 0.0239. I'll keep track of these for later. this one was 0.0239, and this one was essentially 0. Okay, so those are the probabilities from the binomial distribution that answer those 3 questions. Okay, so there's actually another way that I can compute these binomial probabilities within JMP that doesn't involve creating a data table. And I think that this is also a handy way to compute probabilities not only from the binomial but from other distributions. So I wanted to demonstrate that as well. It's kind of buried, so you'll come up here to the Help tab and select Sample Data. From the Sample Data menu, I will select Teaching Scripts in Teaching Resources, and then Interactive Teaching Modules. And what I want in here is this distribution calculator. So for this distribution calculator, it actually does probability calculations for lots of different distributions, one of which is the binomial. So just as before, I need to specify my success probability and my number of trials. Here it has radio buttons for me to specify if I want the probability given like 5 or fewer or exactly 6, or if I want it to give me, if I want it to produce a number of successes for a specific probability from that distribution. And this doesn't make a lot of sense for the binomial case, but it will when we talk about the standard normal distribution. Okay, and so I can give it probabilities that are of interest. So if we come back here to our PowerPoint, we want the probability at 5 or fewer will be colorblind. Well, if I select this option, this will give me the cumulative probability up to a value that's specified. It calls it Q here. So if I type in 5, this tells me the probability that my binomial random variable is less than or equal to 5 is 0.9666, which is what we got from the table, from the data table where we asked it to compute that. The probability that we have exactly 6. Well, notice that I have the cumulative probability, I have the complement of the cumulative probability, I have an interval between 2 points, or I have less than a lower point and greater than an upper point. Well, I can get the probability of exactly 6 by putting in 5 for this lower bound. This will give me the probability that it's strictly greater than 5, but less than or equal to 6. So this is essentially giving me the cumulative probability of being less than or equal to 6, but subtracting off the probability of being less than or equal to 5. And so this should give me the 0.0239 that we saw earlier. And obviously if I want 20 or more, I can put greater than 20 in here, and that reports the probability not as 0 but as something very small. Okay, so that's another way to compute binomial probabilities. Another way that we can compute probabilities from, well, so let's look at how we can use JMP to compute probabilities from a standard normal distribution. So let's take a look at a few examples here. Assume that a random variable z has the standard normal distribution. What's the probability that that random variable is greater than 1.1? So essentially what I'm wanting to do here from my standard normal distribution is figure out how much area is in this upper tail above 1.1. Well, I can do that by the same data table. If I create this is the data table that we used for our binomial calculations, I can just add another column here and do some calculations for normal distribution. So I'll just look at another column and I'll put in 1.1, and I'm going to label this column Z so that I remember that this is for my standard normal. And this next column, I'm going to do some probability calculations in. I'm going to compute the probability that Z is less than little z. So this is actually going to be the cumulative probability that my standard normal random variable is less than 1.1. Essentially, the area that is below 1.1 is what's going to go in here. Now I got to be careful about that because that's not the area I'm interested in. I'm interested in the complement of that. So I'll create another table that calculates the complement of that once I have it. Okay, so I select that column and I go up to the column tab, select formula. This time, instead of discrete probability, I will select probability. And it asks me for what distribution I'm interested in computing probabilities. And I'm interested in computing that for the normal distribution. So I select that here. It asks, the first argument that goes in here is the z value that I just entered into that column. So I'm just going to select this column. Now this does something weird. I have to have this box highlighted, and then to get to the particular normal distribution I want, I have to hit the comma button, the comma key. And so that brings up this mean. By default, it sets it to 0. I can explicitly state that. And then to specify the standard deviation, I will hit the comma key again and specify 1. And now that will compute this for the standard normal distribution. Okay, so what this says is 86.43% of the area of this distribution is to the left of 1.1. Right? So that's not the answer to my question. I'll need to do another calculation, and I can either punch this into a calculator and just subtract this from 1, or I can have this column calculation do this for me within the JMP data table. So I will select subtract, and I will put 1 in there, and then I will subtract from 1 the cumulative distribution for the standard normal. And so I have 13.57% of my area that is above 1.1. So that is 0.1357. All right, and I've got a battery of other questions here for you guys to kind of test yourself on, and I'll do a couple more. What's the probability that z is greater than 1.6 or less than or equal to negative 1.6? Now, because this is continuous, remember, these equalities really don't mean anything. The probability that z is exactly equal to 1.6 or negative 1.6 is 0. So whether you include that equality or not makes no difference for this continuous random variable. Different story for discrete random variables. All right, so I can put in negative 1.6 here. And because I've specified that normal distribution calculation for the entire column, it automatically computes this for me. So visually, the calculation says that there is 0.0548 of the area of this distribution to the left of negative 1.64. So let me draw this. I'm sorry, I said that wrong, to the left of negative 1.6. And that area is 0.054, and I gotta look back here at the table, 48. Okay. So I'm also interested in the area above 1.6. And so I can put that into my data table to get the calculation, but I know by symmetry, because this is a symmetric distribution, the area below negative 1.6 will be equal to the area above 1.6. So this should also be 0.0548. And let's just verify that as we put it in here. I'll put in 1.6. And so what we're going to be interested in is looking at this quantity that tells me the area that's above this z value. Oh, okay, let's get rid of that extra digit 0 there. And so these two quantities are in fact equivalent. I should probably label this column to keep track of the probabilities that are being calculated there. Okay, and so then you can just take your calculator and add those together. When I do that, I get 0.0547, 0.0548 times 2. That gives me 0.1096. So this is 1096. So what's the probability that z will be between 0.4 and 1.21? So what I am interested in here is a line identifying 0.4 and a line identifying 1.21, and I am interested in this area from the standard normal distribution. So that is the probability then that a standard normal random variable will be between 0.4 and 1.21. So the way I can get that out of my table here is to put in 0.4 and put in 1.21. And what that is telling me is the area of this distribution to the left of 0.4 is 0.655. The area to the left of 1.21 is 0.8868. Right? So I can just draw this. To the left of 0.4 was 0.6554. And to the left of 1.21 was 0.8869. Right, so now I don't want either of those areas. Neither of these are the answer to my question, but I can use them to get the answer. I want this area in between them. So if I subtract off everything that's to the left of 0.4, from everything that's to the left of 0.121, I can get this quantity. So then that gives me 0.8869 minus 0.6554, and that gives me 0.2315. So 2315. Okay, another interesting example here is z greater than 2.09 or z less than negative 0.54. So let's draw our lines here. Here is approximately 2.09, and I'm interested in this area. And here is approximately negative 0.54, and I'm interested in this area. Again, this equality really makes no difference, and so I need to figure out this area and add it to that area to answer this question. So I'll put in 0.209 and negative 0.54 into my table. .209 and negative 0.54. And so the area that's above 0.209 is right here, this 0.0183. And the area that's to the left of 0.54 is 0.2946, which gives me 0.3129. Okay, so just like we had more than one way to compute these probabilities for the binomial distribution, we also have more than one way to compute these probabilities for the normal distribution. So if I come back to my distribution calculator, and it's worth working our way back there because it's so buried, just getting used to finding our way there. Under the help menu, sample data, teaching scripts, interactive teaching modules, distribution calculator, I can select a normal distribution, and I can put in the parameters that correspond to the mean and standard deviation. Right now the default is standard normal, so that's good. I can ask it to give me probabilities associated with z values from the standard normal distribution that I'll put in here. So if this radio button is selected, this is giving me the cumulative, this is giving me greater than that value, this is giving me between two values, and then this would give me the upper and lower tails of two values. So let's see if we can verify some of the calculations we've done earlier. With this nice little module here. So the probability that the standard normal random variable is greater than 1.1. So I'm going to choose this button, making sure that my standard normal options are specified. And then I will just change this value to 1.1. And that gives me 13.57, which corresponds to what we computed earlier. What's the probability that z is greater than 1.6 or less than negative 1.6? So I'm going to choose this option. Negative 1.6 is the lower value, and 1.6 is the upper value. And so it identified the two tails as 0.0548 and then added them together to get the 0.1096 that we computed earlier. Verifying the calculations that we obtained here, the probability that z is between 0.4 and 1.21. So we want this middle probability between 0.4 and 1.21, and that probability is 0.2314. So probably a little bit of rounding error that we happened here. So that's not a problem. Okay, and then verifying this last one, that z is greater than 2.09 or z is less than negative 0.54. I'll put in the smaller one first, negative 0.54, and the larger value second. So shading that, there's negative 0.54 and below and 2.09 and above, and adding those together we get 0.3129, and that corresponds to what we computed earlier. Okay, so there you have it. 2 ways for computing binomial and normal probabilities, and as you saw, there are lots of other distributions that can be computed in the same using the same methods. Hopefully this gives you a couple more tools and gets you away from needing to use tables to compute those probabilities. All right, good luck.